Yesterday we were looking at deriving the law of conservation of energy equation, and just to abridge some key points, conservation of energy. We derived the conservation of energy equation from understanding that there are two equations that associated with the work done by gravity. The work done by gravity is equal to change in kinetic energy, and it's also equal to a negative change of gravitational potential energy. In other words, if we have an object in the air, oops, it's gonna get a little cumbersome. If we have an object in the air and we let it fall, let's say that this initial position is 10 meters and the final position is 0, and we let the object fall, we understand that the force of gravity is downward. Force of gravity is downward, and the distance traveled is also downward. So those are both negative, and we understand that work is force times displacement. Since the force and displacement are in the same direction, the work done by gravity is going to be positive, and that's going to be equal to a loss of potential, because at the very top here, as we calculated yesterday, referring to those notes, for this example, we have the gravitational potential energy at this point to be 196 joules. And then the gravitational potential at this point is going to be 0 because there's no height. So 0 minus 196 is negative 196. So we're losing potential energy as we fall downward. And then as we lose the potential energy, as gravity does work WG, work done by gravity, as gravity is doing work to cause a loss of potential, we're actually gaining kinetic. That basically means that the object is moving. So it started from rest, and now it's going to be moving between these two points here. And it can be any 2 points. So the work done by gravity equals to a change in kinetic energy in this context, and it's also equal to a negative change of potential. So since those two equations work for the work due to gravity, we can set these guys equal to each other. Okay, because they mean the same thing. So delta KE is equal to a negative change of gravitational potential energy. And then yesterday, what we also did is, we know mathematically we can just add them together. And then what we get is, after we add them, that those two quantities are going to be equal, the sum of those two quantities will be equal to 0. So delta KE plus gravitational potential energy is equal to 0. It's just a math trick. And so obviously, if we had this equal to 0, we subtract, move one term to the other side, and then that term will be negative. So we're just moving this guy over here to get the sum. So basically what this means is, mathematically it states that the change of kinetic energy plus the change of gravitational potential energy is equal to 0. That means that the sum of these changes is equal to 0, which directly translates into the energy between any 2 points in a closed system is going to be equal to 0. Or in other words, the energy between those 2 points is saved. It's always going to be the same, because the sum of the changes there is no change, because the sum of those changes is equal to 0. That means that the energy is constant. So that's the basic translation of this equation. The energy is constant between any 2 points, especially in a gravitational field. And that's what we're working with. We're working with the force due to gravity. So that's all what this mathematical statement translates to, that the energy is constant. The energy is saved, doesn't change at all. And the stipulation for this is as long as we have this system closed off from the environment, because there are things like friction, heat, and other conditions that can disturb this constancy, that can disturb this relationship. So as long as we close it off from external forces like friction, and generally speaking, the force due to friction will be negligible. That means it's not important. So in that event, the energy is always going to be saved. And so, yeah, no problem, no problem. I know there's some people that we're going to be late. So this is the basic form of energy conservation. And so then after that, we took a step further and we broke these terms down. And we said that delta KE final minus KE initial, delta final minus initial, PE final minus PE initial equal to 0. And then we put in the equations. P final squared and then we put like terms on, their side of the equation, the initial terms on one side, the final terms on the other. And so what we had is equals. And so what we basically come up with is from this conservation statement that the energy is constant. From this statement here, we have derived the case where mathematically we can see that the energy in the beginning, I'll just call this E sub I, is going to be the energy in the end. Since the energy is saved, all of the energy I had at the beginning will be equal to all of the energy at the end. That's what this states. And we also know that this term here, I'm just going to switch these guys around, just convention. So KE initial plus PE initial equals KE final plus PE final. And this term, the sum of kinetic energy and potential energy, is what we call mechanical energy. And this is the mechanical energy in the beginning is going to be equal to the mechanical energy in the end. It's the same thing. We're just giving it a technical term, mechanical energy, because it's associated with some motion, some mechanics. And so that's the law of conservation of energy. And now we're ready to see some more examples. We looked at a couple yesterday using this relationship. So this is the fullness of energy conservation. The energy in the beginning is the energy in the end. And we took a look at that bird problem and another problem from the McGraw-Hill. So what I'd like to do today is take a look at one of the problems in your classwork. If you could just bring that up. And we'll take a look at the first question, and then you guys can go to breakouts and do questions 2 and 3. So yeah, try to get a little bit more practice over this guy. So just make sure you have this relationship understood, and if not, are there any questions regarding it?
I have 2 quick questions. At the beginning of your overview, and you did the example of something falling from 10 meters to 0 meters. You
Yeah.
said the potential energy is 196 joules. How did you get
Mhm.
that?
But yesterday we calculated because potential energy is mass times gravity times height. The height is 10, gravity is 9.8, and then I gave a mass of like 2 kilograms, I think.
Okay, that's just an example then.
Yeah, just an example.
Okay, cool. Also,
Yep.
yeah, that's it. That's it. Thank you.
Mm-hmm. So just to go back over that again, so it's MGH, okay, so 2 times 9.8 times 10 is roughly in 196. So yeah. And then same mass, it can be any mass, 10,000, whatever. So at the bottom, 2 times 9.8 times 0 is just 0. So that's why it's 0 at the bottom. Okay. Okay, so going on, let's take a look at the first question. Please be looking at that one. Let's see. So yeah, I'm just taking a look at that on my screen. So make sure you go to the Google Classroom and pull up this document. We're going to take a look at number 1. Okay, so anyway. So the important thing with these conservation of energy problems is like read it through and dissect what's happening in the beginning, what's happening at the end. What kind of energy is happening in the beginning case and the end? So how do we know beginning to end? Usually, now wording can change and all that stuff. We just have to do a combination of reading the question and actually drawing a picture to kind of make sure that we understand what's going on in the beginning, what's going on in the end, what kind of energy is happening in the beginning, what kind of energy is happening at the end. So reading this question, we have an Olympic runner leaps over a hurdle. If the runner's initial vertical speed, okay, write down the given terms, 2.2 meters per second. If the runner's initial speed, vertical speed is 2.2 meters per second, how much will the runner's center of mass be raised over the jump? Okay. So initially he's running, and then yesterday I stated that the equal sign can be your action, the verb that's going to separate the beginning to the end case. So in this question, the runner's initially, should be an indicator, the runner's initial vertical speed is 2.2 meters per second. How much will the runner's center of mass be raised over the jump? So he's running first, then the action would be, what do you think? So the equal sign will represent what verb in this problem?
It would be leaps.
Yeah, so leaps or raised, that's a good indicator. That would be the verb that will separate a beginning case to ending case. So he's going to be running, then he's going to raise in the air or leap, right? So let's say the hurdle is a certain distance h that we have to find. So running first, so he's on the ground, so the energy in the beginning will be kinetic energy, then he leaps over the hurdle, and so at the end, he's still going to be moving over the hurdle, and he also has a height in the air. So it kind of depends on how you read the problem, but as he leaps over this bar, the final energy will be comprised of kinetic energy and potential because he's moving and in the air. And we're just trying to figure out from this term, the final potential energy term, how high he's actually in the air. So he's running first, he's on the ground. So just put everything out there equals KE final plus PE final. Since it's on the ground, there's no height, so there's no initial potential energy. And so from this final potential energy term, we can figure out his final height, HF, because that's going to be a function of the height. So let's just get the potential energy term by itself, which will be KE final minus KE initial okay, let me pause here a second and take a look back at that. Yeah, actually this problem's a little bit misworded. So what I want to say here is that the runner speed is 2.2. So in the beginning, he just has kinetic energy. There is no height. Then he leaps over the hurdle. So this initial kinetic energy is actually going to be converted only into final potential. It's a bit oddly worded there. So we're going to have just kinetic energy equals final potential. So that makes things actually a little easier. So because you can think about it like this. Running, leaps, at the moment that he leaps over the bar, at that instant, we can say that he's not going to be moving at that instant, but he's going to be in the air. So the energy in the end is potential. So let me just rewrite this. So KEI equals PE final. And then from here, we can figure out the height. So 1/2 m by I squared mgh final. Then we solve for h final, and that's going to be VI squared divided by 2GH. And so that's going to be 2.2 squared, 2 times 9.8. This 2G. Sorry about that. Can't have H in there and solving for H. It's divided by 2G. How do we get that? Because VI squared here, and we're just dividing by G, and we're solving for HF. Okay, and then that'll be our answer there. 2, 18, 6. Okay, so he leaps over the bar. It's by like 0.25 meters. So again, that's what we do. We have to just read the problem, see what's going on initially. Sometimes they'll give you indicator by saying initial something, initial speed in this case, or initial height. Look for the action. The action is going to separate the initial conditions from the final conditions. The final condition is, he's going to be in the air at some point. So that kinetic energy in the beginning is going to convert to potential energy at the end. And once we establish that here, then we can figure out the missing variable. As we saw in this case, it's final height. Okay, so I'll let you go to breakouts for 20 minutes or so. Any questions on any parts of this process? So first thing, read question, identify the energy in the beginning. Find the action. That's the equal sign that separates initial from final. And the stuff after the action is the final energy. And all we have to do is figure out, is the initial energy kinetic energy, potential energy, or both? And same for final. All right. So we're going to do these last two questions, 2 and 3. It's going to be due today by 11. I'll give you pretty much the rest of class to get that turned in.